Push down automata. In this particular lecture, we will cover practically how we can transfer syntax of a language to really a useful language, or like how we can understand the push forward and replacement of expression, so we can build a recurrent cascaded language. This lecture is also available on a podcast, and I would advise you, if you cannot afford having bandwidth of watching the video, please go to the podcast, and I will be guiding through the PowerPoint slide how you can move to which slide we are covering. If you have any questions, just please write them below, and let's start.
This video is subject to copyright owned by Finite. To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
To understand the concept of automata, we have to visualize the following. That's, we have an input string, and this input string will lead, and we have states, and the states will be implemented through a stack. So this is the initial setup, and if you remember the stack, so the stack was top access only structure. So basically you can only see what on the top. So you can only see this particular element here, and you don't access any of the other elements. So the concept is very straightforward. If I have an expression just as a plus b times c, if I have an expression like that, and so what I will do at the very beginning, I will have expression a here, and then I will have the expression b plus c, and then at that point I will remove this expression and get b plus c, and this will be the a. So what I will do is I will compute first the expression, and then I will add the other expression. We will get into details how to do this operation. So to be able to understand the logic, we have to start first with the following annotation. So basically the stack has a stack head, or the top, and this bottom special symbols appear at time 0, which is the very initial, and then you will start to fill the stat. Now, if I want to understand the states will have two different characteristics. One is the input symbol, if it's one symbol, or I can bob out or remove the symbol. So the idea here is, if I start at the very beginning, I have my stack here, and then I will start having the A, and then I have symbol B. After a minute, I need to bob B out and replace it with symbol C. So in this case, the stack itself will have C, A, and C. So this is the idea of the bob symbol. So basically, B replaced by C. This is what we are meaning here. If you want to understand how to solve these problems, you should practice one or two of these problems, and then you should also practice how you can, if you program it or solve it, and from that point you'll be able to complete or understand this topic. So here I have all my, it explains the symbols. So here I have state Q1, I have to move to Q2. I will either has A or B tend to C. So basically, if the top here is B, I will replace B with C, and if the top is only A, I can solve the A. If I have lambda tend to A, means I will remove null, which is nothing, and then I will remove the symbol, I will add the symbol C. If I have transition from B to lambda, mainly I will remove B without any operation. So basically I will bob. And if I do lambda versus lambda, I have no change, which is sometimes you ask, why do you need to have these states? And it's only can be used for synchronization. The idea is when you have a synchronization such that you are being working on two different machines. So let's just start here. And if I have the input signal here, I have the, if I bob from empty stack, the automata will halt. So if I'm trying to pull out from an empty stack, it means an error. The push down automata is a non-deterministic, and it allows only non-deterministic transitions. So I will give you an example in a few. So here is in the example of non-deterministic, I have a set of Q1 which will lead to Q2 or Q3 based on whatever inputs I will have. So in this case, from Q1 to Q2, I have the symbol lambda, or I have B tend to C, where lambda is a transition. So here I have an example. So the example here is the language M, which is A to the power N, B to the power N, where N greater than 0. So I will have from Q node, when lambda or lambda tend to lambda, I will have Q1, and if it's A, it will stay Q1. If it's B or A tend to lambda, it will lead to Q2, and then I will stay in Q2 if it's B or A toward lambda, and then I will go to either null or I will go to the bottom symbol to end up at the final state. So the basic idea here is I will push A's into the stack with this particular symbol here, which is lambda 10 to 8. I will pull A from the stack, or I bob A from the stack where A 10 to lambda, and here I will find the match. So if I want to understand this execution, it will look like following. I have here the symbol, the string A, B, 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 which is N to the power 3. So at time 0, I have to watch my stack here. So my stack will start with the first symbol S, which is the start of the stack. And I'm now in the current, in the initial state Q. So if I'm in the initial state Q, at time 1, I will move to Q1. And then from Q1, I will add symbol A. And then I will add another symbol A. I will add another symbol A. And then when I find B, I will move to Q2. And to find B, I will find out that's A. I will remove A from the stack, and then I will be here. I will keep going, moving A, and then I will accept, because this particular expression is basically accepted. So let's just move back again. I have here my input, which is triple A, triple B. I am here on the current state. I have my stack. So what will happen is I will move, because there is null. Then I will keep adding A, and then once I find B, I will remove A to move to Q2. I will move another A to go to stay at Q2. I will remove another A to remove to Q2, and then I will end up being at the stack, which means I accepted. So the assumption here is a string is accepted if there is a computation such that all input is consumed and the last state is an accepted state. And if we don't care about the stack content at the end of the accepting state, what we care about is we have an accepting state. So here is an example of a rejection state. So I will have the symbols A, B, and I will be looking for the same state diagrams. I will be Q1, I will keep adding A, and then I will move to Q. Then at certain point I move down to S, and I still have symbols here. So in this case it will reject this expression. There is no acceptance computation for AAB. The string AAB is rejected by the push down automata. Another example here is I have this language which basically VVR, which basically the language will repeat itself. So I will be at Q1 as initial state. If I have A or B, I will keep adding to the stack, and then I will move to transition Q1, and then I will remove A's, and then I will end up being in Q. The basic idea of this expression is the push on the stack as I was explaining here, then the middle transitions of the middle of the input, and then I will match. And then once the match is found with the bottom of the stack. So if I want to understand this, I will have a time 0. I will keep adding A. I will keep adding B. There is in the middle of the string, I can go to the Q1, then I can remove the B, I can remove the A, and then I will end up at the accepting states. This will be a rejection states, and here I can keep A, I can add A, I can add B. In the middle, I will move to Q1, then I can remove the B. Now there is no possible transition because I have B as input. The input is not consumed. However, I will if I remove the A, I will end up in the stack. So another computations with on same string, I can do A, B, 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 and then is not accepted state have been reached, so I can stay. So these are two alternative techniques to prove that this expression ABB is not accepted. So there is no computation that accept ABBB, and this is ABBB does not belong to the language machine M. And I would ask you not to get confused, because these are alternative techniques to do the same operation as before. Now, if I look at pushing and bobbing string, if I have an input string here, I can use the bob string and the push string. This particular approach is used to extract sub-expressions or understand sub-expression or sub-language. So example here, I have, if I either have A or I replace EB with CDF. So if I have the input here, this is my stack here. So what will happen if I found the term EB, I will remove it and replace it with the symbol CDF. Now, if you ask why the order in this way, it's basically because we assume the order in this way. If you reverse the order, that B will get first and then and E will get first and B will be the top, it will also work, okay? So this is the bob string and this is the push out string. So this is this equivalent, this particular Q1 to Q2, the bob is equivalent to these two states, and the push is equivalent to these three states. So here is I'm trying to explain, like I can do different state diagrams with different level of details. So if you have type of state diagram which only allow one symbol or multi-symbol, you can still use it. So another push down automata will be W, where W belong to AB star. So here I can define the production rules as or the transitions as A1 to lambda, A00 to 0, and then starting or $sign to $, B will be $sign to $1, B will be 1 10 to 1 1, and A and B 0 length to lambda, and this will be the state diagrams for it. So the execution samples here will be something similar. So if I have the input is A, B, 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 A, remember what we are looking for is to validate that this input is a valid language which work with this particular state diagrams. So if I have my stack here, I'm getting an A, I will get 0, because if I have $sign, it will remove to $sign. And then when I get a B, B will end up 0 to lambda, so I will be remove the 0. And then if I have another B and I have a $sign, which is here, it will end up $sign 1, and then B can end up to remove 1 and add 1 1. A can remove 1. The last A will be remove 1. I end up being a $sign. So in this case, the push down automata works. Okay. Now, I know it's getting confusing, and I know you may not get it from the first time. So I would recommend if you stop the video, go back and review this example again. Some formality of the push automata is a transition function. So if I have Q1 to Q2 and I have the transition function omega 1 to omega 2, in this case the transition function of sigma will be sigma from Q1. If I either get A or omega 1, I will end up having Q2 and omega 2. So here is non-deterministic transitions, which is omega 1, omega 2, and omega 1 leading to omega 3. So if I have the transition function will be q1 a1 omega, it will end up being q2 omega 2 or q3 omega 3. The definition of a finite automata is I will have a machine which has a states, input alphabet, stack alphabet, transition functions, initial state, stack starting symbol, and accepting states. So this is the formal definition of a push-down automata. I always remind you that whoever started this automata was actually a mathematician and scientist. So the mathematicians love to have this particular format. So that's why you always have this kind of definitions, which is you may not be used to it in our current age. There is a current state, remaining input, and current stack. This is defined as a snapshot or instantaneous description. So at any time I can look at the current state, I can look at remaining input, I can look at the current stack content. So here an example of q1. So when I have at this position here on the third symbol, I will be looking at q1. So q1 is the current state. The stack, the remainder is BBB, and the stack has AAA dollar sign. So this at time 4. At time 5, I will be looking at this particular view, and at time, and we can write that from time 4 to time 5, I can do the transition from this state to these states. This is important because the application of that is when you build the controllers and you try to map this to an actual controller states, you'll be able to verify at certain point that your controllers or your machine will actually conclude. In computation, you basically go from Q1, Q2. This will be all the transitions from this particular input. So here I have the input AAA, triple B, and this will show all the transitions with all the stack time. So you can be candidate to a question which say demonstrate the instantaneous description of the following state diagram. So this will be the definition, and for convenience we can start from the initial state to the last state. A language of BDA or a push-down automata will be the language that the machine will accept it. So the initial state of a language starts, the accepting state will start, and a language which can be understood by the machine itself will be a push-down automata language. So here is an example. If I have the initial state here and this is the last state, if the language is AABBB, this is belong to the language of machine which is a push-down automata will do. I have here a symbol of the push-down automata. I proven before that from this symbol to this symbol, I will end up understanding by the language, and therefore LM is the language of a push-down automata. So we covered the push-down automata. If you have questions, please send them to me by email or under this video below. These concepts of push-down automata is very helpful once you start to implement simple PIC or programmable controllers or simple control devices or simple language. It also describes how the compilers, parsers work using a stack concept. Looking forward to hear your feedback, and see you in a following lecture. Thank you.